This tool is about the same idea than speed, but it's for thermal part of the machine. And we're going to see why it's actually very easy. This is the first thing, and where it looks to us the same as speed, is that the input of the geometry is done through dedicated editors. And by the way, you can actually bring in the lamination from speed directly inside Motor-CAD, as well as we will see the losses and everything. So this is the template to define the geometry. And you can see the same type of information as we saw this morning: the slot number, the house diameter, the housing diameter, the magnet thickness, the pole number. There is a slot number somewhere and stuff like this. All of this is here with a little more, because there were things that speed didn't care about. And for example, it didn't care whether the housing was a certain shape or another one, though this is very important for the thermal. It probably, let's see, what else do we have here? I think probably the rest is all also in speed. We can also look at something else you didn't have for speed. I mean, you had it in speed because you had the extension of the interns and stuff like this. But here we have a little more. You can see here the motor can be mounted or not mounted. We have some information about feedback that don't exist in speed, and other things of this kind. And eventually you'll see fins and other things like this. So here we have things like the housing lengths. We have also the shaft extension, because the shaft is important as a thermal sink. Okay. Everything that actually brings a thermal option to the device. So the geometry is done using those dedicated input. Then you just have to select materials and cooling options. We'll look at this a little after. And all the heat transfer data is computed automatically. You don't have to do anything. Once you have the materials and you have the topology, the program is going to develop the thermal circuit with resistance and capacitance and bring you just a slump circuit and solving steady state or transient. This is the circuit as it is developed. So you can see the network, it's more than the 10 we talked about this morning. You can see there are quite a few. We have windings, we have slots, we have actually this is the core, we have housing and stuff like this. We'll look at it a little bit closer after. And then you can solve in steady state, so that's the result would be the temperature in steady state, or in transient, and we will see what we mean by transient. So basically what it does is that it takes the topology and converts it into a network of resistance and capacitance and sources. So for example, if I look at it here, I have all those, here, those are resistance. We have the resistance, which is the tooth, half of the tooth and the yoke. Then we have half of the tooth on the other side, that's going to the stator bore, and then eventually we go to the surface. So here we go to the air gap. Then this is a permanent magnet machine, so we have the, actually it's an embedded permanent magnet machine, so we have the rotor surface, we have actually the magnets, no that's the surface, I'm sorry, surface permanent magnet. We have those capacitance at the surface of the air gap. We have the insertion of energy, so that would be eddy current losses inside the magnet. There is also here iron losses inside the back iron. And here we have the coils. We have 1, 2, 3 layers, 4 layers of the coil with impregnation. That's some of the capacitance. Then we have other resistance and things like this. What can it do? It can actually do brushless permanent magnet, so that would be surface or embedded magnet, exactly the same as speed. It can also do induction machine, single phase or polyphase, actually 3-phase or single phase. And in fact, for the single phase, there is a possibility to change the distribution of the power depending on the way your machine is actually built. Switch reluctance machine. And then we have, I think, what is this, brush machine. You can see the ring here where the brush would be. And the rotor, stator with the magnet on the side actually. We have an inside-out motor, which is not coming. Okay, hold on, it's coming here. Okay, they're all coming at the same time. This is an inside-out motor with the permanent magnet on the outside and the stator in the inside. We have a claw pole machine, claw pole, which is the structure non-null generator, it's sometimes called also. And we have synchronous machine with the DC field. So we can solve all of those. Now, the important part of all of this is not all those topology, but the good part about motor-CAD is all the work that has been done for the cooling. There are people who actually spend the time to actually look at the different type of cooling, whether it's just blown over, it's water cooled, it's any type of spray down, and they have computed all the coefficients to take into account those different cooling. So if we look about this, we have this is totally enclosed, non-ventilated, with different type of design. We have forced convection with many thin channel designs. We can even have cooling on top of it. Through ventilation with rotor and stator cooling ducts. So we have ducts that go through the stator and the rotor. We have water jacket, open and chill cooling, water jacket. And those jacket could be with axial flow or circumferential flow. We have even stator and rotor water jacket. Actually, we have even slot water jacket now. Submersible cooling, so that means the motor is completely submersed. There is a possibility to do wet rotor and wet stator cooling, spray cooling, direct conductor cooling. This is it, it's a slot water jacket. Conduction, radiation, internal and external. So you can see the different type of housing with the fins, different type of fins with the cooling around. We have here a water jacket, or maybe, it's a fluid basically. It could be something else. It doesn't have to be water. And here's same kind of stuff. And so the different housing type we can have just the servo type of machines, or actually this one, kind of the square machine. We have same with actually fins. You can see those different type of fins, kind of radial fins, some that are actually squared, other type of square, all of the things. So you design, you enter the geometry, you define the materials, you select the type of cooling, you enter the losses, and you solve. And once you do this, you immediately have the steady state. And with the steady state, you can see here we have some information about the temperature. So this typical machine here, which is I think the default which is in, at steady state we get about 100 degrees, 110 degrees inside the winding. If I look at the stator here, I go to a little less than about 100, 105. Then I go to the housing, 90, etc. So I can actually follow all the paths of the heat. And you can see that there is something that comes back here to the bearing. Actually, maybe those are the bearing. Then we have something, this is the shaft. And with the extension of the shaft, this is the front. That's actually the flange right there. Another bearing around here. I mean, all of those different things. And you can get this information for steady state, but also, and we'll see after, we can do simple transient or complex duty cycle loads. Simple transient means I'm going to start cooling the machine, looking at how it works, and then see how long it takes to reach a certain temperature. Here are different type of duty cycle, and actually all of those, this is just to show you that all this problem has been, all this work has been validated with measurement. So we can see here, this is, I think, this was an aerospace type of application. And we can see in yellow the computation for motor-CAD, and in red, whatever was measured. So now we have to be careful, because when we talk about measuring the temperature of a machine, you need to know where you're going to take the temperature, because of course it's going to affect very much the result of the measurement. And then you need to look in a critical way when you look at both of those. So, I mean, other validation here, we'll see after what they are. I'm going to go further here. Again, this is just to explain to you the different input. The winding, this is just a diagram that shows you the ratio of copper to insulation. Of course, it's not wound this way. The yellow represents the surface of the copper. The green represents the insulation. You can have those winding, or you can have actually concentrated winding, so which would have a space in the middle that would separate the two parts of the winding. The winding can be different layers. We have here 1, 2, 3, 4 layers. The one I'm showing here is actually only 3 layers. Actually, no, 4. 1, 2, 3, 4. You can see the input of the power in each of them, and then the resistance and capacitance between the different layers. You can enter the layer with just a fill factor, or you can actually get a percentage of copper. You have to be careful putting the M winding correctly, because those are the very important cooling function. Once you put the winding, you can select the cooling method. So here is the sheets where you get the cooling. Now you can see the cooling options. You can have the cooling type. This is totally enclosed, non-ventilated. Then we have totally enclosed, fan cooled, through ventilation. Again, then after you select the fluid. So here it's totally enclosed, non-ventilated. What kind of fluid do we have on the outside? So it's going to be air. On the inside, it's going to be air. If we can have something else depending on what we use to cool. Let's see, also very important part, how is the motor mounted? Is this horizontal, shaft up, shaft down? That's actually going to play, it's going to affect the way the machine cools or heats. Then different type of liquid cooling. What do we have here? We have the ambient temperatures, we have the shaft speed, stacking factors and stuff like this, and other type. If we have a fixed temperature, for example, you have the plate is maintained a certain temperature, or the shaft is maintained a temperature, or something like this. So those are all heat sink, and you need to actually define them. Then you have the liquid. You have different cooling type of liquid, or this is air only. And they basically are described by all those characteristics, and then you can always add as a coolant if you want. The losses, so the losses is where you would actually get them straight from speed, or you can actually get them from flux also, same idea. And you can see all those losses are actually distributed through the different part of the machine. So of course, stator copper losses, no problem. That's just the Joule losses inside the armature winding. We have the stator back iron. Those are the core losses, or stator tooth. So they're basically separated between the back iron and the tooth itself. And if you remember, when you think about the diagram in Motor-CAD, you have an element for the tooth and you have an element for the back iron. Then we have losses on the rotor and stuff like this. But you can also have other losses which may participate in the heat. Friction of the bearing. That's something you can have. You can also add power. I don't know, for some reason your machine is in a hot environment or something like this, and you have some heat coming in. You can have this kind of stuff. And all of those values are defined for a certain reference speed. And then with this reference speed, then we can apply a formula that will compute the power losses at any speed. And why is this important? Because we want to be able to do the duty cycle. So if we want the duty cycle, we need to be able to compute the losses at every type of state. Here is the current distribution in the copper. And then, you know what, most of those you can actually forget. There are so many parameters that you can set in the program. So you can really adapt it to any type of problem you have. But you don't have to adapt to put them. They're already there. So you only change them if you have a specific type of problem. You have something different. You have a machine. Maybe, for example, there is a parameter which is important. It's the interface gap. So when you actually do your stator and you put it inside the housing, depending on your manufacturing quality, they may be stuck together, the stator back iron and the housing, or they may have some ridges. So you can actually adjust the stuff, but once you know how your machines are done, there is no problem. Material properties, so that's the other things you have to put after. So for each of those different parts, housing, aluminum, what do we have? Then cap, aluminum alloy, we have iron for the stator, lamination and teeth, etc. So all of those are entered. They're already there. And you can modify any of those values also. So, by the way, all of those information are used to compute the resistance and capacitance between the nodes. Here is the material database. So when you enter materials, then you can actually enter all those different values and enter any new materials that you decide to. But you can see there are quite a few. And especially there is a base of liquid, which is for the cooling, which is quite good. Here, the interface, I was talking about it. This is actually depends completely on your craftsmanship. How well you know how to do your machine, how well you actually, your tools are, and your skills are, okay? So by default, you can see this interface gap, stator line housing, it's set at 30 microns. That's actually an average value. If you're working in medical and you have really very, very strong condition, probably you can reduce this value. And if you're just doing, you're running somewhere in a shady area, probably then you have to be careful because they're not as stuck together. So you can actually, and by the way, one of the things you can do is if you have a dot, what you can do is you do a sensitivity study of this. So you range this interface gap, and you're going to see how it affects the temperature of your machine. Through ventilation model, so different type of through ventilation, and then you can set the fan characteristic. So it's going to adjust all of this for the cooling and stuff like this. Motor mounting, of course, if it's mounted on a foot or on a flange, this is a heatsink, same idea. So you have to actually set all of those things. That's just to explain that everything is actually color-coded. So the stator is red, the coil is yellow, the magnet is green, the stator, the rotor back iron is blue, this is a shaft, and then we have the bearing and the end cap and stuff like this. Okay, once this is done, you get the diagram from before, and then you can actually get some different representation. Now, let's be careful. When you look at this temperature, this is a 1D type of problem, okay? So that means that this temperature that it computes right here is going to be the same here, well actually, yeah, it's same here all around, okay? Same here. If I take here or here, it's going to be 117.4. If I take this coil, actually there is just a little difference what, because if the machine is mounted horizontally, so it does take into consideration cooling or stuff like this. So you could have something like this, or the layer of the winding also. Then here in this way, there is, now you can have up to 5 layers. So you in the shop, actually no, I'm sorry. So there is a computation which is done in the center of the machine, and now you could have 5 layers in the machine. So if you have something different, you could have actually 5 layers right there. Then once you are out of the stack length, of course you have the end turns, and then you have the flange or the end caps in the front and in the back. Those are the numbers, okay? We don't have a gradient or anything like this. We get punctual information. And as I mentioned before, you can do a sensitivity analysis, or where you can actually rank some parameters and then get the result for those different parameters. And so it gives you some information on how you can adjust some coefficient or the effect of some coefficients. Duty cycle, I was mentioning it before. So what it means is that the machine actually doesn't run all the time. Somebody was talking to me about a spindle machine for a dental application. So the dentist doesn't have it running all the time. It starts, does its drilling, then stops it, takes something else, then comes back to the machine, doing it, goes back. That's a duty cycle. Elevator. The elevator don't work all the time. Sometimes they're stopped. They go up, they go down. In the night, nothing happens. They're very used maybe from 7:30 to 8:30. I don't know about Feng Chia University, but they're different time of the day. Plus, they're different time of the year. There is Saturday, there is Sunday. I don't know, there is Chinese New Year. All of those days are different. So, for example, the people from Otis Elevators, they have redesigned all of their things and they have the full duty cycle over one full year, all in Excel, and you can bring it in. So this one I don't even remember. I think this was an aerospace application, as I said before. So what you can see here, this motor is actually driven by little spikes. We have a high torque, then we have a constant torque, high torque, constant torque, middle torque, then again high, and then this is repeated, then we have a higher torque right there, and then those little spikes again, and then it goes down to 0. And this is actually the speed. Okay? So now we can compute all of this. So you can see this part here is actually the part which is here. So we have a high part, and then we have all those little peaks. You can count them, they're exactly here. Then we have this big peak, here it is. Actually, we have 3, one behind the other, but they're kind of lost. Then we have all the snakes, here it is. This one is this peak. Then we have this part. Then we have this. And guess what? This is a higher torque. And now we actually increasing a different rate. See, before we were going this, now we're going this way. Now we have those few spikes here, and here they are. And now we stop, and here it's cooled off. Okay? So you can do all of this. So you can, for example, if you're designing something for an electric car, but you can have all the driving cycle. They're actually standard driving cycle. The car is in the city, start, it stop, it start, it stop. On highways and stuff like this, you can put this right here and compute the behavior of your machine. Another kind of funky duty cycle. This is an underwater motor. So you use the machine inside the water, and once inside the water, it's cooled by the water around. Okay? Of course, inside the winding warms up to a certain state. So on the outside here, I get, I don't even know, this should be 10 degrees or 20 degrees, the temperature of the water. The coil goes up to 85 right here. Then I stop using the machine, I get out of the water, I put my motor on the side, I wait a couple of seconds, I want to take it and burn my hands. Why? Because here I cut the power, but my coil is still hot, and the temperature needs to find its way out. So the winding inside is going to cool off, but look about the housing. The housing suddenly is jumping because all the temperature is coming to the outside, and I burn my hand. Okay? So you can actually do this kind of computation. Some example of things that were done: motor miniaturization. Today, people actually over-design the machine for thermal reason. We want to make sure that we don't have too much losses inside the winding, so that we don't have too much to evacuate. We make the pieces a little bigger because it's going to take a little more heat out of this. So we can actually work on miniaturization. Impregnation. So I can actually look at the effect of the quality of the impregnation on the winding. Of course, those ones are immediate. The type of cooling, trying to optimize the fin, the spacing between the fin, thickness of the fin. Through ventilation, I just look at this one, submersible stuff. Duty cycles for aerospace, automotive, elevators. We did elevators. Automotive, PMDC, servo, motor duty cycle analysis, outer rotor BPM modeling, transient, winding fault. So there is a fault, brings a lot of losses inside the machine. You need to take this otherwise it's, you need to see what's going to happen to it. So here is an example of miniaturization. Initial machine, 50 millimeter long, active length, housing 130. So we do a new machine. Actually, there were a little more changes on this one. Is that we segmented it so we could have denser winding also. Okay. And now we have 50 millimeter active length. The housing is a little shorter, and we have 34% more of torque for the same temperature rise because of the design, the change in design. It's cooling more efficiently, and it's using also the space more efficiently. So that's just other things that were done on it. It's a new potting type of materials, and just with the potting, better potting, what we found is that there was a 15% reduction of temperature. Potting of the entrance. Another type of application here, it's optimization of the fin on a servo machine here. So you can see that gives you the temperature of the machine, so I'm not too sure of the winding, I think, depending on the spacing between those fins here. And you can see there is a place where it's actually better. Here they're too close to each other. When they go too far, you don't have enough fin, so you don't cool enough anymore. So right there, at something like 8 millimeters, between 6 and 8 millimeters, we have a sweet spot, which is the best position for the fin. So you can do the same kind of stuff. Okay, same thing here. Oh, this is just the torque, rated torque, and versus the stator stock length, and shows the for the different types. But anyway. Some other stuff here. This is the induction machine model. Temperature winding predicted to within 5%. This is a different type of machines actually. All different type of cooling. This is just cast housing. Those two we have actually fins and we have some air going through. This is the cooling in the back. We have I don't remember. This is actually a feed cooling, I think. That's a little bigger, and this is actually water housing, if I'm not water cooled, that's right. So we have a different type of cooling here. This is a totally, it's a through ventilation, actually totally it was forced ventilation. And this was actually the object of a paper that's a little old, it's in 2002. But basically we computed the temperature of the winding for the fan characteristic and all of the things. And we got pretty close to the result, 2-degree difference. I mean, it's not very much. And the adjustment, there were not so many adjustments. What was very important was to consider properly the fan and the way it was working. Through ventilation, I think we saw this as a different type of ducts that are available. We saw the soap bag before, we saw this one, automotive, and I think that's the end of it, and I suggest we take a break. I'm sorry I was a little older, but 10 minutes more. So, yeah, 10 or 15 minutes to break. Okay, thank you. Any question, by the way, before the break? No? Okay, let's take 15 minutes. Flux does have thermal capabilities. And so what we try to do is go, so we usually we compute the conduction, and we can compute losses on convection and stuff like this. So the big important part for us would be actually to add the gap interface and better convection. But here I have the work that was actually presented by my colleagues at our yearly Flux conference in 2012. It was in Roma, and those are my colleagues from CEDRAT, and by the way, there is one name here, it's Sam and me. Julien Verret was a very nice young engineer, and he actually was killed on the road on Sunday. I learned about this yesterday, so I just wanted to acknowledge him as being part of this paper. So in this paper, what we did is that we tried to see how we can estimate the temperature, but using flux. So there are actually different types of getting the value of the temperature. There is a rough estimate, but this is, some people look at the global resistance of the motor, and they say, okay, with this losses, this is what temperature I'm going to get. Then you have things like CFD. CFD is what star CCM is, that was showed to you this morning. So CFD actually requires heavy computing time, and it does also needs quite some training. You have a finite limit, and if you do a full finite limit, you have to mesh everything. And then, of course, once you mesh everything, you have a lot of matrices and stuff like this, and maybe it takes a long time. But no matter what we do, to have a very accurate result, you need to have a good knowledge of the losses. And those losses are better estimated if you do finite limit computation. You have the copper losses, you have eddy current losses, you have iron losses, and you have losses of the magnet. So the idea of this, and by the way, there is another thing, is that when a machine heats up, the magnetic and electrical characteristic of the machine change. The resistance increases with the temperature. The permeability decreases with the temperature. So all of this being set together, so we need to actually have a very good evaluation of those losses. So the idea here is to try to work together the electromagnetic and the thermal in the FEM, but try to do it in an elegant way, quick way. So one of the things you can do is working on a single shot type of work. So what you're going to do is you're going to compute a transient magnetics. This transient magnetics, if you go to just a steady state transient, or you could actually do compute until you are in the steady state, or do maybe an AC steady state or something like this. But the transient is the most important because I want to know the temperature as the machine works. I have in my mind those duty cycles that I would like to do. So I'm going to do the transient, solve for one electrical period, one electrical cycle, and once I have the cycle, I can actually compute the losses for the full cycle. That's what I do here. I'm going to extract the average losses in the copper, in the iron, in the magnet, and I'm going to send them inside the transient thermal, and now I solve the project. So that's what we call a one-shot thing. I have a picture at one point, I'm looking at the thermal picture associated with it. And by the way, there is no connection in time. What I'm saying is that I'm going to apply this forever. You could also go with the direct coupling method. So where you're actually going to have the electric period is going to drive the thermal state. Why? Because if you think about it, the thermal has a time constant which is much larger than the electromagnetic. So I need to do a lot of electromagnetic computation, but I don't need to do the thermal at each time because the machine doesn't rise in temperature. So the best, it doesn't make sense to do this because at the end of the day, I'm going to have 5,000 time steps and only maybe 50 of them are good. I mean, they're all good, but only 50 of them are interesting. So that's not a good way to do it. So now, what the best way probably to work for it is, well, let's do a transient magnetics. We solve for this cycle. We get the extra loss average, the average losses inside the domain, and we solve the transient. That's basically what we did here. But now we're going to do something else. Is that once we have the temperature here, we are going to send back the temperature right here, and now solve for the next cycle with those new temperatures. So now what I'm doing is that I'm updating all the material property inside the magnetics. And the time constant between those two is different because this one has its own time constant, and I choose, I say, okay, I've done so much, or I know that the transient thermal needs information every 1 minute. So I'm going to solve for 1 minute here. Then I'm coming back here and doing only one time step. Then I'm going back with the new temperature information, and I'm solving all of this together. So that's the idea that we're going to try to do, and to control how often we go back to do it. So to do this, what we are going to do is we actually are going to try to identify a different domain. Okay. So for the magnetics, there is no questions. In fact, I think I probably no, it's all by one. In magnetic, I need to have at least one pole, or I need to have so many so that I can rebuild the whole machine. So if I have an integer number of slot per pole per phase, then I can actually do one pole probably. For more advanced winding, maybe I need to do 2 poles. But for the thermal, if really you think about it, I only need 1 pole on the rotor, so this is a brushless machine. But I need only 1 slot. I don't need all the slots. 1 slot is going to be enough for me, because at any given time, all the slots, over a full cycle, all the slots are going to see the same power. The average power in each of the slots is the same. And then the average power in 1 pole on the rotor side is going to be the same over a full electrical cycle. So we're going to, first, so that's the information we're going to address here. So we're going to talk about the motor, describe this motor. We'll talk about the finite analysis. We'll do the transient magnetic application, the transient thermal application, do the coupling and look at the result. And then we're going to see, I just showed you motor-CAD, and we're going to see what motor-CAD would have found for the same machine at the end. So here is the motor, and guess what? This motor has been studied so much. If Toyota was getting just a dime for every time people look at this motor, I think they'd be millionaires. So, but the reason why we actually get so much of it is actually for us in the US, for example, there is a research laboratory in Oak Creek that actually purchased a few of those machines and took them apart and actually tried to understand and measure them. So there is a lot of measurements available for those machines. So anyway, the bus voltage of this machine is 500 volt. The peak torque is 400 Newton meters. The max speed is 6,000 RPM, and the peak power rating. So the peak power rating is actually between 1,200 and 1,500 RPM, and it is 50 kilowatts. The motor characteristic, we have 48 slots. We can see them here. 3-phase wide connection, 8 poles, embedded magnet, neodymium magnet. Lamination, it's so that's M270. It's actually, I think it's like an M19 or something like this. Outer diameter 242 millimeters, stacking 75 millimeters. By the way, we're guilty ourselves of using this a lot. If you remember, last time I showed some optimization problem with this machine. So that's the machine right there, and this is the picture inside Flux. So that's for some kind of a state. I'm not really sure exactly what state it was, but so the finite limits, you know all of this, so we're not going to talk about this. You can see it's actually even done in 3D here. We have all the coils, but you can see the full machine. The parameters that we really need to know very well to get a good result are the VH curve, for example. So what it says is here, we're looking at the thermal side of it. So the VH curve maybe does not have so much effect, but it has effect on the performances of the machine. Then friction coefficient, that's important because it's going to change the way the machine works when you do the mechanical coupling. That's something we don't know very well. And then the other thing is that we need to know them, but they're computed. It's the temperature for the magnetic application and the losses for the thermal application. That's just a circuit that drives the machine. I mean, you've seen this, I'm not going to go back to this. So transient magnetic application, what we're going to do is one pole. And what we're going to put is, if you look at it here, we already starting to think about putting the temperature inside the computation of the coil, okay? That's the resistance of the phase is associated to the temperature. So which means that if the temperature increases, the phase resistance is going to increase. Also, inside the flux density of the magnet, we also have now the temperature which is affecting the magnet itself. And then because the change of the temperature, we're never going to go to 500 degrees. So the BH curve is going to change so little that we are going to ignore the variation in the BH curve with the temperature. For the thermal stuff, so we want to reduce the computation time, but we want to still take into account all the turns of the coils. So what we did here, for the magnetic we didn't do this, but for the thermal what we are doing is that we're actually taking every single bundle and we're going to drive them, to draw them so that we have the proper power distribution and proper temperature distribution. So we are going to assign the power loss to every single of the circles here. And of course it makes sense to know how they're laid inside the slot, because the way they're arranged is going to affect the computation itself. And then for the magnet, so this gives you a picture of the temperature after one cycle, I guess. Or I mean, for the same cycle for a single steady state. And this is actually the current magnet. So inside here we only have, so here we have core loss, we have joule losses, so the ohmic losses. We have some losses inside the iron losses inside the stator. And inside we have eddy current inside the magnet, eventually. And some losses inside the lamination itself, but very little, because in those type of machine we have little. And the losses varying with the temperature, copper, iron, and magnets. That's what I just said. So again, we talked about this coupling before, and that gives you a little information about the time constant. So we do a transient magnetic, we solve for a cycle, and look, we have to solve for 12.5 milliseconds. That's the electrical. I'm sorry. This is a time sampling. So that's the time step that we have here. And this is the time step for the thermal, 60 seconds. So you can see how we have difference and how it makes sense to decouple those two things. So again, we do this, we take the losses, we come here, we solve, we bring back the temperature and solve again. So the losses here vary with the temperature because we bring back the temperature. The effect, if you remember, the coil resistance depends on the temperature, and the parent magnet depends also on the temperature. So the way we do this, because inside Flux today, you can do a direct coupling, but that would not work for this. So the way we do this here, and we talked about it quickly this morning, Marcus, Dr. Anders actually addressed us this morning talking about scripting. Flux actually is based on the Python language, so it's actually an interpreted language. I don't know if some of you have used it, but it's quite easy to use it to do this type of computation. So what we do is we do a script, which is in the Flux language, and then we have some other type of things that goes with it. And inside the script, we're going to call the magnetics, and then we're going to take the results, send them to the thermal, then take the temperature, send them back to the magnetics. That's really what we do. And here is how it works. So initialization at 20 degrees, then we solve one electrical cycle, we extract the losses, copper in one slot, magnet in one pole. With this, we actually compute one slot and one pole. So that's right at the beginning here. And then what we're going to do, so that's the initialization. And now what we do is we're going to actually update the losses. So From here we have temperature. We bring it back, we update the losses on the regions. We actually get also now the stator and water losses. We solve the thermal state, we extract the temperature, send back the temperature to the magnetic, electromagnetic, solve one cycle again, extract again now the losses from the electrical, so the ohmic losses and iron losses and the magnet losses, and come back, update the losses on the regions and calculate the thermal. And so we do this all of the time. So this part is actually only thermal, this part is only magnetics, but then we cycle between the two. We did also something, I don't know if it's done somewhere, but what we did also is that we have to take into account the fact that the air gap, the temperature of the air gap, has to be the same because it's common to both of them. So we have to also cycle to make sure that the temperature on both sides is correct by actually sending some energy on one side or the other. And so if you look at the result, coil temperature versus time, so we can see the rays, and we end up with a temperature of 172 degrees for 173 almost for 580 seconds. And we can see when we are at 580 seconds, we actually have reached the steady state, okay, of the temperature. And the average copper losses, so if I go look on the full cycle, this is the losses in the coil. At 580 seconds, it's actually 726 watts. Okay, so those are computed automatically. So, yeah, basically this is the result we did obtain. And so what we did is we brought this inside the Motro CAD to see if we would find the same thing in Motro CAD. So I'm not going through this, but basically here are the results. And so we got a little more cooling because, okay, I should have talked about the cooling here. So the boundary condition on the magnetics, it's not difficult. Everybody understands we have just periodic cyclic boundary conditions. No question there. The condition of the thermal, here and here, and here and here, we have adiabatic condition. So that means there is no temperature that goes from one side to the other. It's all contained inside this ball. And then on the outside here, we have a heat sink, which would be like it's not a heat sink, it's convection, like we are at the surface of the housing. On this here, it's the surface of the shaft, so same idea. And then in the air gap, I touched it very quickly. What we make sure is that whatever temperature, this is doing convection inside the air gap, so it's heating the ambient temperature, and we make sure that whatever energy comes out of this by convection is the same as the energy that comes out of here. So we adjust this to make sure it's the same. So if one has more, what we're going to do is inject a little energy because it would actually travel through the air gap. And so when we do it into Motro CAD, okay, same idea. So they have the shaft and the housing here. And so if we look at the temperature, you can see we have actually 155, 182, etc. Inside the windings. Let's look at the comparison. So if I look here, in the coil I get 173 degrees compared to 170. It's basically the same. We're not going to talk about differences like this. Stator tooth, 104 to 121. So here it's not quite the same. And in fact, there may be two reasons to this. One of them is actually the way we handle the air gap. The other one may be the way we actually handle the losses on when we get to the housing. But still, for a temperature problem, that's not too bad actually. The magnet 106 for 103, it's perfect. And the shaft 106 for 100, that's also perfect. So the only one where we have to do some work is the stator tooth. And I think it's just due to the way we look at the losses inside the air gap. That's probably the only reason why. So that's just an easy little approximation. So how you can use a tool by taking little pieces and trying to match them together through external script and things like this. So I said those scripts, actually, this problem may become available.